Alright guys, let's continue with our lecture. Today's topic is about the double integrals in polar form. Yes, we are still in this topic of double integrals, and we have done this for 2 weeks already. But today's double integrals is going to be quite different from what we did in the past 2 weeks. In the past 2 weeks, we worked on the double integrals on Cartesian coordinate system. But today, we are going to work on a different coordinate system, and that is the polar coordinates. So we are going to switch to polar coordinates today. And that is why the double integrals that we are going to do today, is called polar form. Well, the good news is if you know what was going on in the past 2 weeks and you know what sweeping variables mean and you did the homework, today's lecture is going to be very manageable to you because it's the same kind of thinking. I'm sorry. It's the same kind of thinking. Alright, so let's get started. Now that we are on the topic of polar coordinates, so let's talk about the coordinates in general. If I remember right, in the beginning of the semester, we talked a little bit about coordinate systems, and we established that when it comes to coordinate systems, the purpose of that is to locate points in the space, right? So when it comes to this coordinates, they all have the same purpose, to tell where the point is, not just by pointing to that point and says, hey, it's right there. It's going to be different. Here, it's going to be specific. We need a name, we need a location. So that is the point of coordinate systems. Alright, so let's take a look at the Cartesian coordinate systems here. So this is used to locate points, any points in space. Well, when it comes to space, so far you see 2 dimension and you also see 3 dimensions. For 2 dimensions, you have Cartesian coordinates and the polar coordinates, which you see in the slide here. For 3D, you have Cartesian again, and you have cylindrical, and also the spherical. But today we are going to focus on 2D. Why 2D? Because this is all about the domain region. Domain region R in double integral. And this domain region that we have done so far, it's on the xy plane, and it has 2 dimensions. So Cartesian coordinates that we talk about today, this is to locate points in 2D space. And by using 2 variables, and that is x and y. With these 2, you know where to find the points. Alright, and that is for the Cartesian coordinates. For polar coordinates, same purpose, which is to locate points in space. Well, here to 2D space. But it's going to use different variables here. Instead of having x and y as the coordinates, it has radius and theta. Now the thing is, these two have the same purpose, locate points, which means that x and y have to be related to r and theta somehow. So the question is, how r and theta is related to x and y? Alright, we are going to find this out right here. Maybe we talked about this in the beginning of the semester, but let's do this again. So this is all about how we switch from xy to r theta, and maybe from r theta to x and y. So here's the first thing we need to do here is to understand the relationship here. Okay, so let's draw a graph. Okay, so that's y-axis. It's always a challenge to draw any graph on the tablet when it's so glassy and slippery. So, but I'm gonna try my best to make my graph look readable and acceptable to you. Okay, so we have this graph with y-axis and x-axis, and let's assume that we have one point that we want to know the location, maybe right here. Without any coordinate system, this point is just there. We just don't know where it is. But if we have Cartesian coordinate system, we can say that, hey, this point has x value right here. Okay, and not just that, it also has the y value right there. So we can name this point, or location of this point, x and y. For example, you can have 1, 2, and you know where to find this point. Maybe sometimes you have minus 50 and 2. You can find those points. Alright, so that is the Cartesian coordinates. Now, let's take a look here. You can see this shape right here, right? You can see a rectangle from this Cartesian coordinate, and that's why sometimes they call the Cartesian coordinates rectangular coordinates. Rectangular, sort of like a nickname, judging by the geometric shape of this coordinate system. Okay, so we have this geometric shape to locate this point. But using rectangular is not the only option here. Well, you can get creative. I want to use some other shape. I want to use maybe a circle. Let's do that. Instead of having this rectangle, I have a circle instead. So starting from here, let's draw a circle. Okay, I'm gonna try my best. Okay, alright, so this is like a quarter of a circle in the first quadrant. So let's assume that this black point is on the circle. So I can say that I'm going to use this red line to locate this point. So with the circle, of course, it's going to have radius. I assume that this time is r. So since this point is on the on the circle, the distance from the origin to this point is also r. Now we have this physical meaning of r, so let's write down this. R is distance from the origin to the point. For example, here the distance is r. Now, if we just use the r as the indicator to locate this point, it's not going to be enough, because the distance r from the origin can be any point on this line. Can be right here, can be any point right here. All these points has the distance r from the origin. So if I want to just point to this location, r is not enough. I need something else, and that is the value of theta here. Alright, so theta is the angle that the x-axis makes to the line connecting from the origin to the point. Okay, so let's put this meaning down. So theta is the angle that x-axis makes to the line. It's kind of long here, but you need to write all of this. To the line connecting origin to the point. So with these two variables, r and theta, we can specifically locate this point in the space. Alright. Now you can see that in this graph, whether you use the Cartesian coordinate or the polar coordinate, it's going to be the exact same point. But now we are going to look at the relationship between this r theta, radius, angle, and x and y. Okay, to understand this, let's use two theories. The first one is the trigonometry, and the second one is Pythagorean. So let's start with the trigonometry. So let's bring up this trigonometry property of cosine theta equal to what? So let's take a look here. So I'm going to ask you to pay attention to this triangle. Alright, this triangle. This is what we are supposed to look at right now. So this triangle, and I want to find cosine theta. So cosine theta is the closed side divided by the hypotenuse side. So we have right here x over r. Alright, and I'm going to move things around a little bit. So we have this x equal to r cosine theta. Okay, and we also have this sine theta right here. Sine theta is the opposite side, or you can say across, right here, divided by the hypotenuse. So that's going to be equal to y divided by r. Move things around, and then you have y equal to r sine theta. With these two equations, let's put boxes around them. Okay. Okay, we have two relationships here from two equations, but it turns out it's not enough. So let's take a look at this. We need more equations, and we are going to use Pythagorean. So Pythagorean, this side, so you are going to see that x squared plus y squared equal to r squared. Alright, that's another one. And let's use the trigonometry property again. And we have this tan theta. Tan theta equal to opposite side divided by closed side, that is y over x. And you can say that, hey, this is theta equal to arctan y over x. So let's put the boxes around this one too. The question is, why do we need all these for? And there is a reason behind that. So let's take a look at the first two, the top two. So top two, it works when you know r, you know theta, and you can find x right away. Right? So same as the other one. If you know r, you know theta, you can find y right away. Which means that the top two is going to let us transform from r theta to x and y. So make a note here, this top one, you know, it's kind of hard to write here. Okay, top one, you know r theta, you know this one, and you can get x and y out. Alright. But down here, it's going to be the opposite. If you know x and y, you can compute r. If you know x and y, you can compute theta. So here, instead of know r and theta, you know x and y, and then you get the r and theta from the equations. So this is like the transition both ways. One from r theta to x and y up here, and the other is from x and y to r theta. It depends on the situation which one you need. Okay, so that is it about the relation between r theta and x and y. So let's move on to the double integrals, which is the main topic of today. So double integrals, let's put the formula right here. So double integrals, we have this, and we have a function, but today I'm going to put a dot right here, 2 dots over dA. The reason I put 2 dots is that it doesn't have to be x and y, it can be something else. Okay, so far we use x and y in the formula here because we only care about the Cartesian coordinate. But today we have this polar too, polar coordinates. So this dot can be, these dots can be x and y or r theta. Okay, so let's work on this a little bit so that we understand why we need both versions. Okay. So let's take a look at the Cartesian version of this formula, and this is something that we have done in the past 2 weeks. So in Cartesian we focus on the x variable and y variable. So we have this formula. We are going to perform double integral of the function in terms of x and y, and let's take a look at the most simple version of this, dx and dy. Okay, so when you look at this this formula, you know right away this is about sweeping x first and then y. So when it comes to Cartesian, we sweep x variable and sweep y later. Well, not later. X and y, and we can reverse the order. Okay, so with this information, let's draw a graph and how the sweeping works here. Alright, from the double integration that we see here, we are supposed to sweep the x variable, which means that we are supposed to specify the starting point and the end point. So here maybe start at A and ends at B. So like this, start at A and ends at B. And after that we need to integrate this with respect to y. And also we need to specify the starting point and the end point of the y sweeping. So we say that, hey, y starts at C and ends at D. Starts at C and ends at D. So if you look at the sweeping, we sweep x from A to B and then sweep y from C to D. So in the end we have this domain region and it has a rectangular shape. Okay? Alright, so with this I want you to take a look at this dx dy. We talked about the meaning of this before, and by now we know that this is equal to dA. dA means differential area. It means an area that is so small. So in this case it comes from dx and dy. So dx is like a distance in x direction, but it's so small, like that. Let's assume that this is small. It looks big here, but dx is supposed to be so small. Now we also have dy right here, distance in y direction but very small. Alright, dy and dx. Of course, if you multiply them together, you have the area of this small rectangle, and we call this differential area. And once we add them up, we can include all the whole region of the domain. Okay, so we know that dA here equal to dx and dy, and we also know that from Fubini's theorem number 1, this is going to be equal to the double integral with the reverse order. Okay, many of you ask me about the reverse order integration for the homework, and you said that I never talked about this. Actually, this is reverse order. We can just it's like switching the order of the integration. Instead of integrating this with respect to x first, we can integrate this with respect to y, and then x. This is reverse order integration. All right, it's not something new or some new technique. All right, okay, so we have this reverse order, and don't forget to reverse the order of the boundaries too. So now y starts from C to D, and x from A to B. Okay, so what we see here, this is the version for the Fubini's. Okay, Fubini's theorem number 1. All right, and that is the most simple form of this double integral. But then we also talk about the Fubini's theorem number 2. I'm not going into the details here, but the whole point of number 2 is that the boundaries are not regular. It becomes a curve, so that we need to use the functions as boundary instead. So for theorem 2, we use functions as boundary instead of constants. Up here we use constant all the way through. C, D, A, B, everything is constant. But for number 2, Fubini's theorem number 2, we use functions instead. And that's why we have, lower function to upper function when you sweep y, and you have left function and right function when you sweep variable x. So instead, right here. Okay, so with this in mind, expect something similar to happen with the polar coordinates. All right, all these here will be translated into in polar form. But before that, before we draw any graph and talk about the formula, let's talk about the basic. Polar coordinates, we work on radius and theta. All right, which means that we are going to sweep radius and sweep theta instead of x and y, but it's the same logic. Okay, so why do we need polar coordinates? It's because sometimes we work on the object with circular or cylindrical shape, and working on polar coordinates is more suitable and much easier to do calculations. So it depends on the situation. So for polar coordinates, it's going to be for circular and cylindrical objects. Alright, so let's take a look at the formula here. So the formula, double integration of the function. Now, the function here is not going to be related to x and y like up there. It's going to be related to the new variables, which is r and theta. And then we have this dA. And we have to perform double integration over a domain region. Now, I need to make this dA becomes to be in terms of r and theta. Just like up here, dA becomes dx and dy. And many of you might say that, hey, dA is dA supposed to be this supposed to be dr d theta. Many of you might say this because up here in the slide you have dA equal to dx dy, and now we move to r and theta. It's supposed to be the same. But it turns out that no, that's not the case for the polar coordinates. It turns out that we have another term right here, extra term, and we are supposed to have r right here. So for dA in polar coordinates, we are supposed to have this extra r. I can just ask you to memorize this and just, hey, this is the way it is, but I think that's not the way to understand math. We are supposed to know why we have this r right here in the formula. So just let's take a look at this this diagram. It's going to take like maybe 5 minutes to know why we have this little r right here. Okay, so let's draw a graph on the left hand side. So our main point here is to understand where this r comes from. So all right, so let's go to the basic here. Polar coordinates, it's about sweeping a variable. Okay, so sweeping the radius. So I'm going to change this a little bit, take this r out. Now, you can see that in this integration, we have order of integration. We need to start integrate this with respect to r first, and then d theta, which means that we are going to sweep the radius first. So let's say that we start at this radius. Radius means the distance from the origin. So this r equal to a, and we are going to sweep the radius to r equal to b. So in this double integration, r is going to start at r equal to a and ends at radius equal to b. Okay, now after that we are supposed to work on the angle. We are going to sweep the angle. So what does it look like? It's going to be evolving or orbiting around the origin. So and also in an anti-clockwise direction. So theta is going to sweep like this. So starting from this r equal to b, theta sweep anti-clockwise around the origin. Well, let's go all the way to here. Alright, everything is gone. Let me draw again. Okay, sweeping the theta anti-clockwise around the origin. Okay, this looks better. Alright, so this theta starts at alpha and ends at beta. So that is the boundaries for the angle sweeping. So we have this theta equal to alpha and theta equal to beta right here as the endpoint. So what does this region look like? So this sweeping of angle doesn't apply to just r equal to b, it has to apply to r equal to a as well. Sweep like that. So we have this line at theta equal to beta. So we have this shape. I'm going to highlight this. Sweep the radius just like above. Right here, above here, we sweep x and then y. And down here we sweep radius already, so we sweep the theta. So we have this shape. Okay, this r equal to a right here, it can be any value. It can be r equal to 0. If r equal to 0, that means it starts from the origin. Alright, you look at this shape. This is sort of like a slice of pizza with one bite. Well, I want you to see how this region looks like when compared to the Cartesian coordinate. So it's going to look like this. Now, back to our main goal. Understand where this r comes from, this r. Right? To understand that, let's take a look at the something similar to the Cartesian diagram. Something similar to this is the differential area, the small area in the case of polar form. So let's take a look at what kind of shape it looks like in polar coordinates. So in polar coordinates, we are going to sweep the r variable a little bit. So let's take a look here. Sorry for the color, it's different from up there. So I'm going to use red to make it easier to see. So starting right here, I'm going to sweep a little bit in r direction. So going away from the origin in terms of radius, so goes out like that. Oh, that's not nice. Let me fix that. It's supposed to be straight. Okay, so go out straight. Oh man. Alright, again, try again. Okay, straight like that. Anyway, and then we sweep the theta like that, and then do the same thing right here. So we have this shape. And as you can see, this is not a rectangle, because we have curve at the outside here and we have this curve at the inside. But the point is, we have to find what is dA. What is dA in terms of all these variables. Okay, so to do that, we need something extra. So let's take a look at this circle with radius r. Let's assume that this is a circle and with radius r. And then if I ask you to find the area of this piece, the area of just this, and this piece has the angle of theta, area equal to what? How are you going to find that? This little area, this little pizza? Well, we can use the ratio to find the area of this. So we know from long time ago that if theta equal to 2 pi, it means the whole circle, right? Area equal to what? Area equal to pi r squared. Something we learned from long time ago, maybe from elementary school, maybe middle school, I don't know. But this definitely everyone know about this. But here we don't want the 2 pi. We want just one piece. We want theta. If theta is just theta, what is the area? So we can use this ratio to find out. So theta is, the area is going to be equal to theta times pi r squared over 2 pi. So here we have this cancel. So we have a right here equal to 1 over 2 theta r squared. So we have this formula to find the area of this piece. Any theta you can put in here and you can get this area out. And as you can see, if you put 2 pi, you get the pi r squared out of this formula. So let's use this to find out about this differential area, this thing. Okay, I'm gonna leave it like this so that you can see up here. Okay, we want to find the area of this little piece. So let's say that it looks like this little piece. I magnify it a little bit. Okay, and let's extend this to here and extend this to there, which means that this point is the origin. Okay, and we want to know the area of this. So let's assume that at this point it's r1 away from the origin, and this point is r2 away from the origin. Okay, and we are going to find out about this area. So area here is going to be equal to the area of the outside, the whole piece, right? The I'm going to say big piece. Big piece. And this small piece. To find the area of this blue piece here. Okay, we are supposed to find the area of the big piece, the big slice, minus the area of the small slice, a pizza, whatever you call. So this is going to be the area of the big piece. That is going to be 1 over 2 theta. We use the formula from up there. So theta and r squared here. So r here is equal to r2 squared. That is the big piece, right? And then we minus this with the smaller piece, 1 over 2 theta r1 squared. This is like calculating the area of the ring, right? You find the area of the circle, and then you subtract the area of the smaller circle, and then you find the area of the rings. But this is just part of the ring. Okay, so let's work on this a little bit more. So let's take the common terms out. 1 over 2 right here. Oh, by the way, I'm going to change this a little bit. I'm going to call this angle delta theta. So let's fix this. Put delta right here and delta right here. So I take the common term 1 over 2 out, and I take the common term delta theta out on the right hand side. So what is left in the middle? I have r2 square minus r1 square. Alright, and then I can perform the factorization. So I have 1 over 2. This is front square minus back square. So it's going to be front plus back times front minus back times d theta. Now that we have it in this form, we can do something more with this. So r2 minus r1. r2 minus r1 is definitely this. The distance from r2 to r1, and that is delta r. So this r2 minus r1, we have delta r. Now let's take a look at this. 1 over 2 times r2 plus r1. What is that? Well, you can think of this. 1 over 2 times a plus b. This is the average value of a and b. In other words, this is the middle value between a and b. So this middle value between this thing, between r2 and r1. So middle value right here, also right here. So I'm going to use the center of this piece. So this thing is r, right in the middle of r1 and r2. So this is equal to r. Alright, and then we can do this a little bit more, and we can get this a equal to r times delta r and delta theta for this little piece of, I don't know what to call this shape, but I just highlighted it. So this piece. But of course, we don't want this piece to be too big. I want this to be as small as possible. So this area becomes a differential area, which means that the delta r becomes so small, it becomes dr, right? And the delta theta becomes so small too, becomes d theta. And that's why we have this formula for dA in polar form. And that's why we have this extra r in our formula. So here, polar form with extra r. Alright, so you know where this formula comes from, right? Not just, hey, polar form, it has to have r. That's not the answer you are supposed to give to anyone. You can explain about this, that I know where this r comes from. Alright, once this is done, let's summarize about the formula that we have to use in this lecture. Okay, go back to the origin. We have this form, double integral of f Here we work on the polar coordinates. So F has to be in terms of r and theta. And now we know dA equal to r dr d theta. So let's put that. Well, okay, this is the general form, dA. dA first, okay, and over any region. And then we put information into everything. So double integration of F, r and theta. dA becomes r dr d theta. In this order, we sweep the radius first. So radius starts from A and ends at B. And then for the theta, starts from alpha and end at beta. Let's put a box around this. Okay. This is the first formula. And this is the equivalence to the Fubini's theorem number 1 for the Cartesian coordinate. So similar to, equivalent to. Theorem 1 that we learned from last lecture. Okay. Actually, if you look at this dA here equal to r dr d theta, but it's also equal to r d theta dr. It means that, okay, let me fix that. So d theta dr. It means that the order of integration, you can do it with respect to r first and then theta, or you can do it with respect to theta first and then r. So you can put a note here, order can be reversed. Right. You can choose to integrate this with respect to theta first, but usually when it comes to polar form, they usually stick with this order. You are going to see this much more often, r dr d theta, instead of d theta dr. Right? More common. Okay, so we have that first formula equivalent to Fubini's theorem number 1, but since we have Fubini's theorem number 2, we are going to have something similar to that. So when to use this advanced version? When your shape looks something like this. Let's draw this small graph. Before, it's just circular shape, but sometimes you have something different. Well, let's put the angle first. So far it's circular, but sometimes you get something like this. Alright, it's possible. So with this kind of shape, you can't just specify r to be a constant, because in this case you sweep from the inner curve to the outer curve, inner curve to the outer curve, inner curve to the outer curve, and all the way through. It's no longer just A and B like before. We sweep from the inner curve, we are going to call that G1 theta, to the outer curve, which is G2 theta. Right? And this makes the formula changes a little bit. So double integration again, F, R, and theta, R, dr, d theta. So instead of sweeping from A to B, just like before, we sweep from inner function, G1 theta, to outer function, G2 theta. And for the angle, same thing, over the whole range from alpha to beta. And that's all the equations you need to understand this lecture. 2 equations, 2 formulas, not equations, I'm sorry, 2 formulas. Okay, and this is equivalent to Fubini's theorem number 2, where we have irregular shape for the boundaries. Equivalent to Okay, and this is for irregular shape, irregular shape boundaries. Alright, once you have these two formulas, you are ready to do all these examples. After this, it's all about the experience and practice. So let's do some examples today, maybe 3, and do some more in part 2. I'm going to split this video into 2 parts, otherwise it's going to be too long. Okay, let's start with the example 1. So what are we supposed to find here? So let's take a look at this problem. We are supposed to find the area. Okay, this is area. Okay, and enclosed by the curve r squared equal to 4 cosine 2 theta, definitely polar coordinates, polar form. In the first quadrant, so we have x-axis and y-axis come into play. So first quadrant by double integration. So you can't use the single integration to find this area. They ask you to use double integration. So when it comes to double integration and area, you know what to do. This is from last lecture. So area. Okay, and we have this, let's put the formula down first. So far we have this double integration of f r theta dA, and so far we know that this is the volume under the function surface over domain region, right? If we want to make this becomes an area, want to make this formula for an area, we need to make the function value equal to 1. So that is the key to solve this problem. So that is the first thing we are going to do. So you can see that looking at this this diagram, it has an irregular shape. It's not so simple like we saw before. So definitely we are going to use the second formula. So here expect to use this formula. Double integration r theta r dr d theta, and we need to know the inner function g1 theta and outer function g2 theta, and for the angle it's going to sweep from alpha to beta. Okay, now our job is to find what this is. Functions in terms of r and theta, inner function in terms of theta, outer function in terms of theta, alpha and beta. We are supposed to find all these 5 terms. So let's make a note here. This is inner function and this is outer function. Well, in order to find all these 5, you need to draw the diagram. Well, without the diagram provided you in this example, it's kind of hard to know what kind of shape this is. R squared equal to 4 cosine 2 theta. So for this kind of problems, they are supposed to give us the diagram to continue. Now, with this diagram provided to you, you can start by finding out about all these 5 terms. The first term that you know right away is this f, r, and theta. Okay, is equal to this. Sorry, hold on. Okay, this is about finding the area. I'm sorry for the pause. Finding the area. So the f function value is supposed to be 1. So you found the first one right here, and it comes from this. We are supposed to find the area. Alright, now let's find out about g1 theta and g2 theta. What is that? So in order to find out about that, we need to look at the region and how the variable sweeps across the area. So here we can see that this we sweep from 0 to the curve, 0 to the curve, 0 to the curve, and all the way through here. So that is one thing to know. One thing we know here is that we sweep from 0 to the curve. This is what we know. Sweep from origin to the curve. Alright, which means that starting point, this is the origin, g1 theta. That is the inner function. It's going to be equal to 0. Radius equal to 0. Alright, and then to the curve right here, that is g2 theta equal to the curve. And the curve that we are looking at here is r squared equal to 4 cosine 2 theta. But here we are integrating with respect to r. So we can't just use r squared right here. So let's use r equal to square root of 4 cosine 2 theta. Alright, so this is the curve that we are looking at. So which means that g2 theta equal to square root of 4 cosine 2 theta, and that is the outer curve, inner function, inner curve, and this outer. Now what we need to do, the rest we need to do is to find out about alpha and beta. Okay, this is about sweeping the angle. So let's take a look here. We are going to sweep the angle from here to here, here to here, here to here. So you can see that we start sweeping from the x-axis. Sweep the theta from x-axis, which means that the alpha here is supposed to be angle of 0. Okay. Now what about beta? It turns out that beta here is a little bit tricky to compute. Looking at this, each line sweep differently. But is this supposed to be pi over 2? Is this supposed to be pi over 4? So we have to find out about this range of angle. So in order to do that, we are going to use these equations. R squared equal to 4 cosine 2 theta. One thing we get from this equation is that both sides has to be greater than 0, because this is r squared, supposed to be greater than 0. This terms on the right hand side supposed to be greater than 0, which means cosine 2 theta supposed to be greater than 0, and also means that 2 theta supposed to be less than pi over 2 and greater than 0 in the first quadrant. And after that we can see that theta here less than pi over 4 and greater than 0. Notice here, if your 2 theta is greater than pi over 2, cosine of that angle is going to be negative. Well, you can think of this, you can check these values by yourself, but I give this value to you right now. So let's just use this. So we can see that the range of theta here starts from 0 to pi over 4, which means that the maximum that we can go is the whole range is this. So this is beta. So here we have the last term, beta equal to pi over 4. Well, some of you might be wondering how I get to this. So just take a look here. Cosine 2 theta greater than 0. If cosine of any angle that is greater than pi over 2, it becomes negative. So this angle 2 theta has to be less than pi over 2. Right. Sorry, I might not make it clear here, but you can think about this. Take your time and think about this. So we have all these terms. All right. Okay, function, done. Inner function, done. Outer function, done. And the range for the angle, done. And for the starting point and the end point. Now we can do the integration. Okay, so we have this double integration. All right, so the function that we are working on is 1 because this is about the area. So we have r d theta. Inner function is 0 from up here. Outer function, square root of 4 cosine 2 theta. And now for the angle, start at 0 and ends at pi over 4. So after this, it's just the regular integration. So let's integrate this with respect to r first. So the first thing I get from this is r squared over 2. Right. So the first step, we integrate this with respect to r, so we treat all the theta to be constant. But lucky here, we don't have theta to worry about. So here, after I get this, I need to evaluate this at 0 and 4 cosine 2 theta. All right, and then don't forget to integrate again with respect to theta, starting from 0 to pi over 4. Okay, let's put everything in. So 4 cosine 2 theta square becomes square root of 4 cosine 2 theta. It goes to here and it gets square, so I get just the inside of the square root. 4 cosine 2 theta divided by 2 minus another value, 0 goes in. 0 goes in. Everything becomes 0. So I have this 0. All right, we have some cancellation here. So I have 2. All right, integration with respect to theta, starting from 0 to pi over 4. Now let's continue with this. Integration of cosine 2 theta with respect to theta. Integrating cosine, you get sine 2 theta, but with the reverse chain rule. So you have extra 2 here. All right, and we also have the 2 coefficient of 2 in front here. Now we see this see cancellation here too. All right, and we evaluate this at 0 and pi over 4. So this equal to sine pi over 4 goes in, becomes pi over 2, minus sine 0 goes in, becomes sine 0, and that's equal to 1 minus 0, and that is 1. So this 1, don't forget that this is area, so don't forget the unit. This is unit square, and this is the area of this little piece. All right, this is area equal to 1. If they ask you for the whole shape, this sort of like a bow, the whole shape, area, whole area equal to 4. Well, 4 times of the values we just got, right? Okay. Okay, and that is example 1. It's all about understanding the sweeping of the radius and angle. So you can see sweep of the radius like that. From the origin to the curve, and then the angle sweep from the x-axis over the whole range. X-axis over the whole range. And the tricky part is this beta, that you need to do some thinking on that in order to get this whole range right here. Okay, but I think it's manageable. Okay, that is example 1. I don't know how long this video has been, but let's do 2 more and let's stop for this part 1. Okay, example 2, what do we have to find here? We are supposed to perform this double integration over xy. Okay, this is going to be different from example 1 because in example 1 we find the area. So function is f. Function is equal to 1. But here, function fxy is not equal to 1. It's equal to x and y. Okay, and over a domain region bounded by, so this is about R, bounded by what? The first one, x squared plus y squared equal to 1. So you see that, hey, this is a circle of radius 1. Y equal to x and y axis. Alright, how am I going to start with this? Well, the first thing you need to do always when it comes to domain region, you have to see the graph. From example 1, we were given with the graph, so we don't need to do any drawing here. But in example 2, they don't give it to us, so let's draw that. So we have this graph. The first one is the first equation is the circle of radius 1. So let's draw a circle here. Okay, this is the worst circle ever. Let me fix that. Okay, let me try one more time. Okay, a little bit better. I don't want to erase and do it again. So that is the first curve, and then we have one more curve right here. Y equal to x. So a straight line passing through the origin with a slope of 1. And we also have this y-axis right here. Okay, so with these 3 lines, we can see that the area that we are supposed to study is this. So let me fix this curve to make it, yeah, okay. Alright, this is 1/8 of the circle. Definitely looks just like a slice of pizza here. And they want to work on this domain region. Okay, and then they give us this function surface fxy. So today we are going to use the double integration in polar form because we are looking at a domain region with circular shape. So you can see that circular shape here, which means that it's more suitable for the polar form. So let's use the formula that we talked about before. Function in terms of r and theta, dA we know is r d theta. And let's use the advanced one. So the sweeping of the radius starts from the inner function, that is g1 theta, up to outer function g2 theta. And the angle sweeps from over the whole range, starting from alpha to beta. Alright, and once again, our job is the same as example 1. Find out about all these terms: f, g1, g2, alpha, and beta. So let's start with this f in terms of r and theta. We need to know about this f in terms of r and theta. But it turns out that they give us x and y. And we can't use this right away because this is x and y. So we need some translation from Cartesian coordinate to the polar coordinate. So we are going to use the relationship that we talked about at the beginning of this lecture. So this is equal to, I'm going to save some space and move to right here. So we need this f of function in terms of r and theta, but we have x and y given from the problem. So let's do some translation. From the equations that we have at the beginning, we have 4 of them, and we know that x equal to r cosine theta and y equal to what? R sine theta. Alright, with this we can see that we have this f in terms of r and theta equal to r square sine theta cosine theta. So all good? You want r and theta? Right here, r and theta only. Okay, the first one is done. Now we need to find out about this g1 theta. Okay, g1 theta equal to what? To do this, to find out about this, we need to know how the variables sweep in this case. So let's take a look here. Sweeping of the variable in terms of radius starts from the origin to the circle, origin to the circle, origin to the circle. So here, sweeping, from the look of this, we know that we sweep from origin to circle. Let's translate this into function. So origin means that the radius equal to 0. So the inner function is equal to 0 in terms of radius. Okay, and outer function, alright, this is the circle. We know that outer function is circle, and this circle is x squared plus y squared equal to 1, right? We cannot use this because it's in terms of x and y. So we need to do some transformation from this Cartesian variables to polar variables. So from before, we know that this x squared plus y squared equal to r squared. So this we have r squared equal to 1, and we can say that r equal to 1. You might ask me, what about minus 1? Well, in terms of radius, we always talk about the positive value, so we omit the negative value here. So this we have r equal to 1, which is the radius of this circle. So here the circle radius equal to 1. Alright, now alpha and beta. Alpha is the start of the sweeping of the angle. So you can see that angle starts sweeping from here, ends at here, here ends at here, and you can see that the starting point here is pi over 4, right? Because of the line y equal to x, and it sweeps to anti-clockwise to pi over 2. So from this you know right away alpha start from 45 degrees or equal to pi over 4, and beta, which is the end point of the angle sweeping, that is 90 degree, that's equal to pi over 2. Right here, starting at 45 degrees and ends at 90 degrees. Once we have all these terms, function, inner function, function surface, inner function, outer function, alpha and beta, we can start doing the integration. Okay, I have some space here. So let's do the integration. Double integration, just like before. Function surface, here we have r squared, sine theta, cosine theta. And for this, after this is dA, and we know it's r dr d theta. Now inner function, we have found that is equal to 0, and outer function is r equal to 1. For the angle, starts from 45 degree pi over 4, ends at 90 degrees pi over 2. Okay, let's perform the integration here. So this pi over 4, pi over 2, 0 and 1. Let's combine r here, r squared and r. So we have r cubed sine theta cosine theta, and we are going to integrate with respect to r first and then with respect to theta. Now with this, let's integrate this with respect to r. So here you see r and theta in the function, but we are integrating with respect to r, so we are going to treat this theta as constant. It doesn't change in this process. So we just focus on this r cubed, which we get r to the 4th divided by 4. Sine theta cosine theta. Nothing changes here, and we need to evaluate this at 0 and 1 and integrate this with respect to theta starting from 45 degrees to 90 degrees. Okay, I'm going to take the common terms, take the coefficient out. This 4 comes outside. This becomes 1 over 4. I need to save some space here. Okay, equal to 1 over 4. Integrate of pi over 4 to pi over 2. Inside, I evaluate this r to the 4th and sine theta cosine theta at 2 values. So 1 goes in. So this becomes sine theta cosine theta, and then 0 goes in. Everything becomes 0, so minus 0. And integrate this with respect to theta. Alright. Okay, I'm going to continue on this side because I ran out of space. Okay, I'm going to continue here. Sorry for the mess. Okay, now we need to do this. Integration of 1 over 4 integration from pi over 4 to pi over 2 sine theta cosine theta d theta. Now you can see that integrating sine theta cosine theta is not so simple. Well, you have done this in Cal 1. When you see something like this, product of one variable and it's non-linear, you need some technique in order to integrate this. So let's try some technique. The first technique that you always think about is the substitution. So what about we let u equal to sine theta, which means that du by d theta equal to cosine theta. Let's try that and see whether it's gonna help us solve this problem. Here we have du equal to cosine theta d theta. Now let's move this u into the equation. So we have this equal to 1 over 4. Nothing changes here. Integrate from pi over 4 to pi over 2 of u. Now u goes in as sine theta, and I leave cosine theta the way it was. Now d theta. Oh, okay. Let's do this. Sorry, this is supposed to be d theta equal to. This is supposed to be d theta equal to du divided by cosine theta. So let's substitute this into the equation here. So we have d theta and d theta equal to du divided by cosine theta. And it turns out we got lucky in this case. We get a cancellation of cosine theta. Okay, and all we need to do is to integrate u with respect to u. So here we have this 1 over 4, just the same, and then we integrate u with respect to u, we get u squared over 2. And we need to evaluate this at pi over 4 and pi over 2. Okay, I think some of you might see something wrong with this. You can see that pi over 4 related to x variable. Oh no, sorry, to theta variable, and pi over 2 this is theta. But what you see here, this is u. So when you use substitution, don't forget to translate it back to the original variable. So you have here pi 1 over 4. I'm going to take 2 out, 2 becomes 1 over 8. So this is sine u equal to sine theta square. Now you can substitute, you can evaluate this at pi over 4 and pi over 2. Okay, so everything's go in. 1 over 8 stays here. Pi over 2 goes in here. So sine pi over 2, that is 1. So we have 1 square. Minus pi over 4 goes in. Sine 45 degrees, that is 1 over square root of 2. And we have square here, so we have 1, well, I can put everything here, 1 over square root of 2 square. Alright, so we have this 1 here, this we have 1 over 2, so we have 1 over 8 times 1 over 2, and that's equal to 1 over 16. And that is the answer for this example. Okay. So don't forget to draw the domain region to start the problems. Okay, let's try one more. Example 3. I'm getting tired here, but let's do example 3 and we can continue with more examples in part 2. So example 3. So what are we looking at here? We are supposed to find the volume. Okay, volume, expect some double integration. Below the function surface, okay, so they give us fxy. Above the xy plane, so this is about the domain region. Between the cylinders, okay, x squared plus y squared equal to 3, and another cylinder. Okay, looking at this is a circle of radius square root of 3, and the first one, circle of radius square root of 3, and this is a circle of radius 2. So you expect that, hey, we are looking at some domain region with some circular shape. Circular shape. Maybe polar form is better. Alright, this is some expectation at the beginning when you read the problems. So we are going to do this double integration, but the first thing you have to do is to draw the graph, the domain region. Without the graph, you just don't know what to do. So let's start this. Okay, so we have this circle. The first one, circle of radius square root of 3. Circle r equal to square root of 3, and this circle r equal to 2. So let's draw that on this diagram. Okay, we have 1 here and 2 here, 1 here and 2 here, 1, 2, 1, 2. So let's draw the circle of radius 2. Okay. Okay, this is a circle. Okay, and we also have a circle of radius square root of 3. So this is about 1.73. So maybe something around here, 1.73. Okay, I need to practice on this more. I just can't draw this circle nicely. Okay. Okay, this is the best I can manage right now. All right, so this is the area that we just that we got from the problems, and they want to find the volume over this domain region. So this ring. Looking at this shape, you know right away if you use the Cartesian coordinate and sweep x and y, it's going to be a nightmare, right? You have to do this x and then y so many times. But if you switch to polar form, you can do this problem much easier and much quicker. So let's take a look here. With this kind of shape, we are going to sweep the radius starting from the inner function to the outer function, inner function to outer function, like that. Inner function to outer function. And then after that, we are going to sweep the angle. I'm going to use green here. Sweep the angle starting from x-axis anti-clockwise. So basically sweep the whole circle. Okay, let's keep that in mind and translate this into math. Once again, we are going to use the formula, the advanced one, function in terms of r and theta. dA is r, dr, d theta. R starts sweeping from the inner function g1 theta to the outer function g2 theta. For the angle, starts sweeping from alpha to beta. So let's translate what we just found out to all these terms. Okay, the first thing we need to find out is about this function in terms of r and theta. So you can take a look here. We want this. Okay, I'm going to save space right here. Function equal to function in terms of r and theta. But right now we have this z equal to x squared divided by x squared plus y squared. So we can't use this because it's in terms of x and y, so we are going to do some translating here. So this is going to be equal to x equal to r cosine theta, but that has to be square. X r cosine theta square plus y, that's r sine theta square. Okay, so what do we have here? So with this, we can see that f of r theta equal to r squared cosine theta square divided by r squared cosine theta square plus r squared sine theta square. You can see that we have these common terms. Cancel r square, and r square. And now you see cosine square plus sine square. And I think everybody knows that this is equal to 1. Alright, so this equal to 1, which means that the function that we want to use here is equal to cosine theta square. Okay, so we are done with the function, and now we need to find out about this inner function g1 of theta, and we know that this inner function is this line. Starting of the sweeping of radius, starting from this circle. So this is circle of r equal to square root of 3, which means this is equal to x squared related to x squared plus y squared equal to 3. We need to translate this into r and theta. And from Pythagorean, from before, you know that this equal to r squared, which means that r equal to square root of 3. So we have this inner function, radius equal to square root of 3. Now outer function, g2 theta, same thing. The outer circle, which is this outer circle. So that is a circle of radius equal to 2 equation x squared plus y squared, that is the second one, equal to 4. So from this we get that r equal to 2. And we can see that this g2 theta equal to 2. Now for the alpha and beta, alpha, starting point of the sweeping angle sweeping. So let's take a look at the sweeping of the angle here. So we sweep the angle, start from the x-axis, and we go all the way around the origin and comes back to the original point, which means that we start from the angle of 0 and ends at angle of 2 pi. Everything is ready. Function, surface, inner function, outer function, alpha and beta, the boundaries for the angle. Now let's do the integration here. So here we are supposed to perform double integration. Okay, of the function surface we found out to be cosine theta square. Cosine theta square, r dr d theta. And inner function, that is square root of 3. Outer function, that is 2. Alpha, starting of the angle sweeping, 0, ends at 2 pi. Okay, now let's integrate this with respect to r first. Alright, so I'm supposed to integrate this r. So I have this r square over 2 cosine theta square. I have to evaluate this at square root of 3 and 2. And with this, I have to integrate one more time with respect to theta. And theta from 0 to 2 pi. Okay, let's continue. I'm going to bring the coefficient 1 over 2 outside. Integrate, same thing, 0 to 2 pi. 2 goes in as r, so I get this 4 cosine theta square minus this square root of 3 goes in, minus square root of 3 square, it becomes 3 cosine theta square. Alright, and I'm supposed to integrate this with respect to theta. Okay, so what do we have here? We have 1 over 2 integrate 0 to 2 pi. So 4 cosine theta, cosine square minus 3 cosine square, so we have cosine theta square right here, d theta. Okay, so with this you can try substitution, but it's not gonna work out really well here. So in Cal 1 you learn that when it comes to sine and cosine with some power like this, it's gonna be better to reduce that power to 1 if you can. When you leave it to power of 2, it's hard to integrate directly. So let's try to make this power of 2 goes away by using the trigonometry property. Cosine theta square equal to 1 plus cosine 2 theta over 2. So if you use this instead, it doesn't have the power that you have to worry about. So let's put that in, equal to 1 over 2 integrate 0 to 2 pi of 1 plus cosine 2 theta over 2 d theta. Alright, so I'm going to take 1 over 4, this 2 outside, it becomes 1 over 4. Integrate of 0 to 2 pi, 1 plus cosine 2 theta d theta. So here we have this integrate 1 with respect to theta, you have theta. Integrate of cosine 2 theta, you have sine 2 theta, and reverse chain rule, you have 2 right here. you have to evaluate this at 0 and 2 pi. And don't forget the coefficient of 1 over 4 outside. So this is equal to 1 over 4. 2 pi goes in, this becomes 2 pi. Alright, 2 pi goes in, sine of 4 pi. Sine of 4 pi, that is 0. Minus 0 goes in to theta, and 0 goes in as to sine 2 theta, that is sine 0. So we have this plus 0 here. Turns out most of these terms become 0. So in the end, we have this pi over 2 as the answer for this problem. So to summarize, it's all about drawing the domain region and find out about the sweeping of the radius and the sweeping of the angle, as you can see here, the thing that we just did. And then after that, it's just the regular integration. Sometimes you have to apply the trigonometry property, okay, and some techniques that we have learned in Cal 1. So I'm going to stop this video right here. We have some more examples. Example 4 and example 5. I'm going to continue on these two examples in the next part. It's going to be more challenging and advanced. So okay, let's wait for that. Bye for now.